Now I'm going to mention something that I haven't said in lecture before, which is how feature scaling can sometimes accelerate the convergence of your gradient descent algorithm. So what I mean by that is if I take my data, my training data, and I scale it, that is, I'm going to center it by subtracting out the mean and then divide by its standard deviation, then my data is now in standard units, as we heard in data 8. So our bias terms are all still 1, and I should note we're not centering and scaling our bias term, because if we center the bias, it will be 0, because the mean of a bunch of 1s is 1. So you subtract out the mean, your bias term goes away, so we don't touch that one. But each of my radiuses, instead of being values like 10 or 12 or 14, they're now telling you how many standard deviations above or below the mean you were. Now I could do that manually using code like you did on an earlier homework or lab, I forget which, or I can use the Scikit-Learn standard scaler. How does it work? Well, you create an object called a standard scaler, you then fit it to your data, and all this does is it computes the means and the variances of each of your columns. And then I have a little trick here where I say, please ignore the bias term. So this function assumes that there's a bias column and xtrain in the 0th column that you give it. This is a little hackish, but it works well. And so then ultimately you end up with a scalar that ignores bias. If you apply the scalar, it has a function called transform that will scale appropriately. That is, we'll do this exact same stuff we did up here. We end up getting the same exact scaled data now having been computed using standard scalar. So I'm just mentioning this because you're more likely to see people do this than to actually compute means and standard deviations and divide through, because this tool already exists. Okay, so great. I've scaled and centered my data. Now what? Well, if I run gradient descent on the scaled training data, it will be very fast. So I'll just run it, and you see that it completed very quickly, less than half a second, and it also got a pretty good result. The norm of the gradient when it was done was quite small, and if we compare the average cross-entropy loss for the beta on the unscaled model with the scaled model, you see that our scaled version is actually even better. Now the beta you get back is different, right? Before it was something like -14 and 1. Now it is -0.7 and 3.5. So it means something else because we're in different units. But overall, the prediction is slightly better, it looks like. And to give you a rough sense of why it behaved better, why it was so much faster, we can look at here, this is the Quiver Plot, showing that if you pick a particular beta 1, beta 2, that the gradients are roughly equal, the two components of the gradient can be roughly equal in magnitude. Whereas in our version before, we had almost vertical lines everywhere. Now we have just a nicer surface for optimization. So really the details here are a bit beyond the scope of our class. All right, so continuing along. Now that we've seen this idea of scaling and centering our data, I should mention one reason to do that is that gradient descent will be faster, but another is it also makes it possible to do regularization, which we're going to do at the very end of this video set. So regularization, remember, you have to make sure that you scale your data, because otherwise terms which have relatively small features will end up, they need large betas to be useful, but regularization will squeeze those betas down. So we want to standardize our data to make sure that regularization does not unfairly penalize features that are relatively small. Okay, so now let's talk a little bit about the various ways that we evaluated the quality of classifiers earlier in this lecture. And so this code here is just going to compute the accuracy of a given beta on a given data set, okay, and for a specific threshold. So for example, if I look at our unscaled model's performance on the unscaled training data, I get back an accuracy of 87%. That is, 87% of the tumors were properly predicted on the training set using the beta that I computed with the unscaled data. Using the scaled data, which had a slightly better mean cross-entropy loss, we see that we get 86.9%. So there's one example that we did not get, that we got in the other case. Now that might seem a little strange because we said the scaled model actually had better cross-entropy loss. And that's true, but it just so happens that after thresholding, we did slightly worse here. Okay. We can also look at the test set performance, which is what really counts. And so here I'm actually going to look at my test set. So this creates the feature matrix or the design matrix for the test set. And we see when we run this code that we have 60.8% of the observations are malignant. Why am I doing this? This is not accuracy. The reason I'm doing this is I'm saying that the two classes are relatively balanced. We have about as many benign as malignant, a little more malignant, but that means accuracy should be useful. If you have a situation where one of your classes happens 99% of the time, like spam ham or something, then accuracy is not a useful metric. So I'm just defending my use of accuracy here. So on the test set, if we look on the test set, we find that the unscaled model, it gets 91% accuracy. So what this is doing is applying beta 1F to the test set. And if we look at our scaled X1 data, same thing happens, 90.9%. Okay. So that right there, you'll note maybe a little surprising because the training set we had 86% and on the test set we had 91%. So we're actually doing even better on the test set than the training set. Why is that happening? Just random chance. I think the test set just happens to have easier to classify examples. This being a relatively small sample, sometimes that happens. Where did I get, one thing I want to note real quick is that in order to assess the accuracy of our scaled model, I had to produce a scaled version of the test data. And so I did that using the same scaler. There's a note here for those of you who are very careful readers that the scaled version of the test data does not have zero mean and unit variance. And that's because it was scaled using the training set. And it's very important that when you scale your test data, if you're doing a scaled version of a model, that you scale the test data into the same units from your training set. So the means and the standard deviations that you're subtracting and dividing by, they have to be from the training set applied to the test set. That's so that they're in the same units. That's the intuition there. All right. So continuing along, looking more at the quality of our models, what we see is this function here is going to give us just a convenient way of summarizing the training and the test accuracy for a given model. So just to summarize everything we've been doing on our scaled data, if we use our best known beta for the scaled model, we get 87% training accuracy and 91% test accuracy. Okay. So for comparison, and to wrap up this video, let's see how a model does that is trained on all available features instead of just the radius and the intercept. Okay. So we're going to do this by defining a design matrix that uses all of the features. And this function here, what it does is just drops only the answer. Why are we dropping the answer? Well, if we include whether it's malignant or not, it's pretty easy to compute or predict whether it is malignant or not. So I'm getting rid of the answer, but everything else is kept there. So our new design matrix, instead of having two columns, has 31. The first is the bias, then the radius, then all that other stuff we haven't been using. Now, as we did earlier, we are now going to scale this data, which I hope will make gradient descent converge more quickly, and also because it'll be nice for regularization later. So what I'm going to do is I'm going to use our train scaler that ignores bias function from earlier, which will train a scikit-learn scaler. Okay. Then I'm going to take that scaler and transform the training and the test set and give us a scaled version of the same data up here. So for example, the scaled version of our training set has a 1 in the bias column because we're ignoring the bias. But then the radius is no longer 12.63 for this observation, but minus 0.4, saying that it is 0.4 standard deviations below the mean. And that same thing has happened for each of these other features, and we end up with data that is in standard units. Okay. So now, finally, we want to compare the model we get for our 2-feature model to our many feature model. Okay. So a reminder that well, I guess we'll call it a 1-feature model. Our 1-feature model, which only used a bias and the radius, it was able to get 91% test accuracy and 87% training accuracy. If we use this design matrix instead to train our model by giving this matrix to our gradient descent algorithm, we end up getting, I'm not going to rerun it because it's slow, it will get 100% training accuracy and 94% test accuracy. So this is just the same set of observations and the same algorithm, just a matter of which features we've provided to our model. Now this 100% accuracy is very interesting. It's interesting because that's as good as you can do, but it also means our data is linearly separable. That is, in this 32-dimensional space, there is a 31-dimensional hyperplane that separates the two sides. Just like whenever we had our flower model, where we had 2 parameters, there was a 1-dimensional object, a line, that separated them. So now in this much higher dimensional space, there is something that separates all the malignant examples from all of the benign examples if we use all 32 of our available dimensions. Okay? So, as a result of this, what we'll get are betas that are quite large. And if we let gradient descent keep going, they'd get even bigger. Now, what do I mean by large? Well, we look at this beta and we see that it's 16. That's actually pretty big for a logistic regression model. Think about it this way. If you have an observation where this feature is 1 standard deviation above the mean, that will get multiplied by 16 and then exponentiated. That's a pretty big number. So as a result, we have a model which is far too confident, and so we need to employ regularization or some other technique in order to keep the model complexity under control and keep these betas from being gigantic. And so we'll see that in the next and final video of today's set of videos. Plus, also we'll see a little bit about evaluating classifiers using ROC curves and precision recall curves, just briefly, just to bring everything together. And then we'll summarize the day. All right.